Yeah, thanks, Michelle, for the very kind introduction and for the invitation. It's a pleasure to speak in this seminar series. So I'll be talking about the asymptotic safety paradigm for gravity and matter. You can think of the paradigm as the attempt to go beyond effective field theory, while in some sense staying in spirit as close as possible to effective field theory, and not being exotic in the sense of trying to minimize the number of exotic ingredients, both in terms of physics as well as the framework. And so our starting point are two very successful effective theories of nature, the standard model of particle physics on the one side, and Einstein gravity on the other. Both of those are tremendously successful in experiments and in observations. There are, of course, a few places where some tensions are showing up, but so far there isn't really any conclusive indication that these theories are insufficient to describe nature at the scales where we are currently testing them. However, if we try to go beyond and if we use these theories to ask the question, what are the fundamental building blocks of nature, then we run into an impasse because neither of those two is ultraviolet complete. You can see that in the case of Einstein gravity in a breakdown of predictivity, and that is directly tied to the perturbative non-renormalizability that the theory suffers from. And perturbative non-renormalizability means that there is an infinite number of counter terms that needs to be introduced. Each one of them comes with its own free parameter, its own coupling constant, and so you end up with an infinite number of free parameters, and so with a breakdown of predictivity. In the standard model, the impossibility to really go far into the UV, that is signaled by the occurrence of Landau poles in the scale-dependent couplings that occur in the Abelian hypercharge and in the Higgs-Yukawa sector. And so overall, these two theories cannot yet be taken all the way to sort of really fundamental scales to tell us about the fundamental building blocks of nature. And of course, they are also incompatible, as far as we know, beyond the effective field theory regime. So in the effective field theory regime, we can actually compute quantum gravity contributions to the interactions of elementary particles. But by the very definition of that regime, those effects are completely tiny. And if we want to understand the effects of quantum gravity on matter, in a regime where these effects become stronger, then we can't do that within the effective field theory framework. And now the question that I'll be asking is, well, whether asymptotic safety could help with these points here and improve the situation somewhat. So let me start by giving you an introduction into what asymptotic safety is. So at its heart, asymptotic safety is all about a new symmetry principle, and that symmetry is a quantum version of scale symmetry. And if you actually look around, then there's lots of examples of approximate scale symmetry or self-similarity that we do encounter in the natural world. And in some sense, what asymptotic safety is all about is asking whether scale symmetry could also really be a much deeper principle of nature. And we're asking that question in a quantum field theoretic framework, so in the presence of quantum fluctuations. And of course, what happens in the presence of quantum fluctuations is that these break scale symmetry, the theory becomes scale dependent and features a non-trivial renormalization group flow. And that means that the couplings become dependent on the energy or momentum scale, and that effective dynamics changes as you go from scale to scale. There is a way to recover scale symmetry, and that is at renormalization group fixed points, where the renormalization group transformation that tells us how the effective dynamics changes from scale to scale, that reaches a fixed point, which means that the scale dependence vanishes. And that can be done in two ways. One of them is asymptotic freedom, which in some sense is a bit of a sort of trivial restoration of scale symmetry in the sense that it switches off all of the interactions. And so it switches off the effect of quantum fluctuations, and you are in some sense back in a classical incarnation of scale symmetry. Asymptotic safety is an interacting renormalization group fixed point at finite values of the couplings. So it's a genuine quantum version of scale symmetry. It really relies on those interactions being present and quantum fluctuations being there to achieving the scale symmetric regime. Now, asymptotic safety, in some sense, you can think of that as its ingredients, taking whatever your favorite effective field theory is, and then adding UV quantum scale symmetry. Now, of course, these two ingredients don't necessarily go together. Not every effective field theory can become asymptotically safe. It's particular effective field theories that can be made asymptotically safe by such a quantum scale symmetric point. If you achieve this, this goal of combining the two, then that gains you two things. First of all, it gives you the possibility to UV extend or complete the effective field theory. And on the other hand, it also gives you predictivity. In an effective field theory, of course, we in general have an infinite number of coupling constants. At low energies, most of those don't play a role, but in principle, all of them are there. And asymptotic safety is a way of providing you with predictivity at all scales in this setting. Now let me explain how both of these things are achieved. So the possibility to UV extend or complete is probably a little more obvious from the sketch down here. So if you have couplings which just run towards constants, and you're no longer changing the theory as you change the scale, then in particular, you won't get anything like Landau poles, and the theory can be consistently extended towards higher and higher scales. Now, the other question, that of predictivity, that is probably a little less easy to see. So what happens more specifically is that if you take whatever your preferred effective action is, that has a bunch of different operators in it, and the interaction strengths are parameterized by these couplings. In an effective field theory, all those are independent free parameters. Now, in asymptotic safety, you're demanding that all of these infinitely many couplings, they start out at a renormalization group fixed point in the ultraviolet. And as a consequence of that, there are actually relations that relate these various couplings in the theory to each other that follow as a non-trivial requirement out of scale symmetry. And this is what gives you predictivity in that setting. And since this will be a really important part in the important point in the second part of my talk, where I will talk a little bit about phenomenological implications, therefore I'd like to take some time now to explain in more detail where exactly the predictivity comes from. So at the heart of the predictive power of asymptotic safety is a different behavior that running couplings can have. So in general, we already know that we can't live at an asymptotically safe fixed point. We don't live in a scale symmetric regime. And the way to see that is to just look around you and observe that there are distinct physical scales in nature. And so this means that if fundamentally the world is quantum scale symmetric, then there has to be a scale at which we depart from this asymptotically safe regime and a non-trivial renormalization group flow sets in. And now this departure can't just occur along arbitrary directions in the space of couplings. It can occur along the so-called relevant directions. The relevant directions are those where a small perturbation away from scale symmetry grows under the impact of quantum fluctuations, and quantum fluctuations drive you away from a scale symmetric regime as you go towards larger scales. So these relevant directions, a simple model for that, a very simple toy model is this beta function where alpha star is a fixed point value, and where at this fixed point, the slope of the beta function is negative. So the critical exponent is positive. And this is exactly what encodes this property that quantum fluctuations drive you away from quantum scale symmetry in this direction. As a consequence, if you demand quantum scale symmetry in the ultraviolet, this doesn't allow you to say anything about the value of the coupling in the infrared, simply because you can see you can depart in arbitrary directions. You have a sort of whole range of infrared values of the coupling available. And therefore, such a relevant direction gives you just a free parameter, in some sense similar to what you would have just in the effective field theory setting. Now that's different if you flip around the sign in the beta function here, because on a technical level, that changes the slope of the beta function and turns the critical exponent negative. And what that means physically is that now quantum fluctuations drive you towards quantum scale symmetry, even if you depart from it. And as a consequence of that, if you demand quantum scale symmetry in the UV, then that automatically fixes the infrared, the low energy value of the coupling from scale symmetry. In this very simple example that I'm showing you here, the infrared value is just also fixed to be the fixed point value. In examples with more couplings, this will be different. But the key point here is that whenever you have such an irrelevant direction, then by demanding quantum scale symmetry in the UV, you fix the infrared value. So from scale symmetry, you get a prediction for an irrelevant direction. So in general, we have to combine these two simple examples. So in general, we are working in a space of all of the infinitely many couplings that you have in a generic effective field theory. And now assume that there is an asymptotically safe fixed point sitting here, then that will have what is technically called a UV critical surface, which is just the surface within which quantum fluctuations drive you away from quantum scale symmetry. And therefore, what you're getting out are predictions for the values of the irrelevant couplings, those which are infrared attractive under the flow. So in this specific simple sketch here, if you fix the values of G1 and G2, let's say by doing an experiment, then that gives you the location within this critical surface. And from that, you get a prediction for the value of the coupling G3, even away from the fixed point. And so if you want sort of an analogy to think about that, think about quantum scale symmetry like being the Cheshire cat that is no longer realized in the infrared. It's no longer present, but an imprint of it remains, namely relations between couplings or predictions of the values of couplings that remain in the infrared as a consequence of quantum scale symmetry in the ultraviolet. You can also think of that as, in some sense, just the predictive power of a new symmetry. So whenever you give yourself a Lagrangian and you impose an additional symmetry on that, then that will give you relations between various couplings in the Lagrangian that are necessary in order to satisfy that symmetry. And in some sense, the situation is similar here. If you want the Lagrangian to be such that you can realize quantum scale symmetry in the UV, then that constrains the values of the parameter in the Lagrangian at all scales. Now, let me give you a very specific example for asymptotic safety that also demonstrates its predictive power. And the example here is sort of a very non-exotic example. It's just a standard 4-dimensional perturbative quantum field theory. So no gravity yet, no exotic ingredients. So in fact, the theory is just a simple Gauge-Yukawa theory in its structure, in some sense, quite close to that of the standard model. So in this Gauge-Yukawa theory, what we're interested in is the gauge coupling alpha G and the Yukawa coupling alpha Y. And the gauge coupling alpha G for a non-Abelian gauge theory, the one loop coefficient B here, that is negative if the number of charged matter fields is sufficiently low. But if you crank it up enough, that coefficient changes its sign, and then you have lost asymptotic freedom and you get a positive beta function around the origin. Now that, on the other hand, then gives you the possibility to get an interacting UV fixed point. For that, you need the two-loop coefficient to be negative. And now it turns out that that can be achieved in the presence of a finite Yukawa coupling in the presence of this term here. And in turn, in the beta function for the Yukawa coupling, the effect of different quantum fluctuations can balance out at finite values of Yukawa and gauge coupling. And all of these coefficients, B, C, D, E, and F, they depend on the number of charged fermions and scalars. And what Daniel Littim and Francesco Sannino realized in 2014 is that you can find representations if you go to an SUN gauge theory in the large number of color limit, and you also go to a large number of flavors, then you can find settings where all of these coefficients take signs such that you get asymptotic safety. And so this is then what the corresponding flow diagram looks like. So here we have the two couplings on the axis, and we see a fixed point of the renormalization group flow here, a non-trivial one, an asymptotically safe one. And you can also see that it is infrared attractive in one direction and infrared repulsive in the other. So you have two couplings in this sketch, but you actually only have one free parameter, because if you demand asymptotic safety in the UV, then that determines that you have to lie somewhere on this line here as you flow towards the infrared. And so the Yukawa coupling is calculable as a function of the gauge coupling at all scales as a consequence of asymptotic safety here. So what this simple example shows you is sort of two things. First of all, that asymptotic safety, although it's, as far as we know, not realized in the standard model itself, asymptotic safety is still not a sort of completely exotic paradigm that can only occur in three-dimensional quantum field theories or in the presence of quantum gravity. It can actually occur in quantum field theories which are very similar to the standard model. And secondly, what this example also shows you is that in asymptotic safety, you can have more predictive power than you would have sort of in an effective field theory treatment of this model, where both of these couplings would correspond to some of the free parameters of the theory. So with that, let me now come to the search for asymptotic safety in gravity matter systems. And let me first motivate why it is that I'm thinking about gravity matter systems and not just either gravity or matter on its own. So the argument is that if you want to understand the microstructure of space-time, it's not in some sense safe to neglect quantum fluctuations of matter, because quantum fluctuations of matter do impact the microstructure of space-time. And so a pure quantum theory of gravity is presumably bound to look quite different than a theory in which you have accounted for the presence of matter. Now, conversely, matter and gravity are always coupled. And so if you want to really understand the fundamental constituents of matter at really, really small scales, then at some point you will run into the regime where the gravitational interaction between those will become important. And so if you want to really understand the fundamental building blocks of matter, you do need to account for their gravitational interaction. And so therefore, it's really the interplay of quantum gravity and matter that is interesting and illuminating to focus on. If you want more of an analogy, then you could say we really want to understand sort of the full picture of the universe, all of its constituents. And if we think just about quantum gravity, then that in some sense is just like staring at the blank canvas. Whereas if we just think about matter, then we're just looking at the color pigments, and doing either of those will not allow us to understand the full picture. So therefore, we are looking at gravity matter systems. Why in asymptotic safety? Well, the motivation here picks up on what I had on one of my first slides. Einstein gravity on its own is perturbatively non-renormalizable, which means that all of these various couplings, including those of higher order curvature terms, they need to be introduced as counter terms, and they do become, or are expected to become, dynamically important at the Planck scale, which leads to a loss of predictivity. And this is exactly where asymptotic safety might kick in and restore predictivity. On the other hand, in the standard model, we run into a problem at trans-Planckian scales where there are Landau poles, or where we expect the non-perturbative triviality problem to show up. And I do find it quite interesting that the scale where the standard model itself is signaling to us that it's breaking down and that it needs new physics, that scale actually happens to be a trans-Planckian scale, because that opens up the possibility that the only new physics that is needed to provide us with a UV extended or even completed standard model, that could actually be quantum gravity. And then the standard model, that's of course not a fundamental flaw, but it still has 19 free parameters, quite a few. And of course, we could wonder whether maybe some of those could become calculable within this new paradigm of asymptotic safety. So you can, in some sense, think of asymptotic safety as following in a historic tradition where we are asking whether a new symmetry can somehow help with the situation. And of course, there is this tradition of asking this question in terms of grand unification or of supersymmetry. And now sort of in this tradition, you can think of asymptotic safety as asking whether quantum scale symmetry could also provide some progress here. So what I will be discussing for the remainder of the talk is then sort of the steps in the search for asymptotic safety in gravity matter systems. So I'll first give you a brief introduction to the technical setup, and I don't want it to go into any technical details. I just want to give you really a sort of superficial idea of what the techniques in the setting are and what the open questions related to that are. And then I'll briefly review this current status of asymptotic safety. And that, of course, will really just sort of be a sketch of a relatively rapidly evolving research field. And I would also like to really highlight what the open questions in that setting are at the moment. And then in the final part, I'll focus on what I think is one of the most interesting aspects of asymptotically safe gravity metasystems, namely the potential predictive power of that setting. And so I'll give 3 examples for that: the Abelian gauge coupling and the Yukawa sector within the standard model or standard model-like settings. And then I'll end on the question whether we could learn something about dark sectors from this paradigm. And if there's any questions at this point, then maybe this is a good point to interrupt before I go more into the details of this. All right, so I don't see any questions right now. Also nothing in the chat, so then let me continue for now. So let me start by giving you an idea of the technique that is being used here, and that is the functional renormalization group. And let me first give you sort of a more physical or intuitive understanding what it does, and then I'll tell you a little bit more about the technicalities. So in the functional renormalization group, this is a tool that integrates out quantum fluctuations as a function of scale, starting in the UV regime and then integrating quantum fluctuations all the way towards the infrared to get a sort of complete path integral. And starting in the very far UV with gravity matter systems, we are essentially asking the question whether there is an asymptotically safe fixed point regime. And in such a regime, you would have most of the dimensionless versions of the couplings becoming constant, but it could also be a possibility that some of those couplings still approach an asymptotically free regime. So at an asymptotically safe fixed point, it's not necessary that all the couplings are interacting. It's very well possible that some of the couplings still become asymptotically free. Now, if there is such an asymptotically safe fixed point regime, then there also needs to be a scale at which we leave quantum scale symmetry, and that is expected to be the Planck scale, because that's a scale where quantum gravitational fluctuations that generate the scale symmetry. The Planck scale is where those decouple and where we would therefore deviate from quantum scale symmetry. And in fact, once the dimensionless Newton coupling leaves its fixed point value, it actually goes to 0 pretty quickly. And that's just a question of, that's just a consequence of its canonical dimensionality. So the Newton coupling, the gravitational coupling, has dimension -2, which means that its dimensionless version scales with the energy scale squared. And therefore below the Planck scale, that goes to 0 very quickly. And since the Newton coupling parameterizes the strength of gravitational fluctuations, these then decouple at that scale pretty quickly and automatically. And then below that scale, you just have a more or less standard matter renormalization group flow that might then allow you to end up with something that is more or less standard model-like. And of course, then one of the questions that are really interesting to ask is whether, as a consequence of quantum scale symmetry in the UV, you are getting predictions or calculations for the values of some of these couplings as sort of imprints that would then also in turn allow you to test this hypothesis of quantum scale symmetry in the far UV, even though, of course, experimentally currently we cannot access Planckian or trans-Planckian scales. So at a more technical level, the functional renormalization group achieves this integrating out of quantum fluctuations as a function of scale as follows. It does that by introducing a mass-like regulator term or cutoff term into the path integral. So here I'm showing that for a simple scalar field. And that a new term is a quadratic term. So it acts like a mass term in the Euclidean. But that mass term is one that depends both on the RG scale K and on the momentum of the mode that you're looking at. And it's chosen such that it vanishes, such that it's 0 for modes with momenta larger than K squared. And so these are integrated out and they do contribute to the effective dynamics. Conversely, modes with low momenta, they get this additional mass-like suppression term. And so therefore, they are not yet contributing to the effective dynamics. Now, the big advantage of this setup is that it actually allows a reformulation of the path integral into a functional differential equation. And that functional differential equation is one that gives you the scale dependence of the effective dynamics. That equation is quite broadly used in and out of equilibrium statistical physics, in quantum many particle systems, for instance, in cold atoms, in various questions in high energy physics, and in quantum gravity. And the way that it is used in quantum gravity or in the search for asymptotic safety is as follows. In step one, one searches for fixed points by solving this equation, and that the scale derivative vanishes because those points identify quantum scale symmetry. And then in a second step, if such a fixed point is found, then that provides an initial condition for the renormalization group flow from high scales all the way to k equals 0, where all quantum fluctuations are integrated out and where one can understand what are the infrared or the physics consequences of quantum scale symmetry in the UV. And in practice, the way that this is done is that there are beta functions for the couplings in the effective dynamics that can be calculated in truncations of this effective dynamics. So let me now talk a little bit about the status of asymptotic safety, first just in pure gravity, where this idea, of course, goes back to a paper by Steven Weinberg from the 70s. And then this field started to become more active with Martin Reuter's seminal paper on the functional renormalization group. And the corresponding ultraviolet fixed point or universality classes is now typically called the Reuter fixed point. And there are quite compelling indications for the existence of that fixed point in pure gravity. So what I'm showing you here are really just a few selected examples of a much larger body of literature and research. But what you're seeing here is that various truncations of the effective dynamics that account for various additions to the effective dynamics, they have all been tested. And what you see here are the critical exponents, and those give you the information about how predictive that setting is. And in fact, there are 3 critical exponents which are positive. Those correspond to the free parameters. And then the remaining ones are all negative or come out negative in these studies. And this is what gives you the predictive power of asymptotic safety. Now, in the case of pure gravity, that predictive power is maybe at the moment not so useful in the sense that observationally, it's of course really difficult to gain access to the couplings of these higher order gravitational terms. And so at the moment, it's difficult to make use of that predictive power in actual observational tests.
Can I stop you there with a question, Astrid?
Yeah.
So can you comment a little bit about because you're very nicely describing what it's a very beautiful program of how the things go to a fixed point, but then the problem is always in actually calculating reliably what the beta functions are, and the problem in an effective field theory, like you said, is that you lose control of the loop expansion. Can you comment on what controls your ability to evaluate what these critical exponents are, for example, and what the beta functions are, given that the derivative expansion is kind of breaking down? How do you control that?
Yeah, so I think you have actually seen my next slide, because I was just going to comment on one of those aspects. So first of all, because you mentioned the derivative expansion, that is actually only one of the techniques that is being used. There's also a large body of work that uses a vertex expansion for gravitational fluctuations, and that produces results which are quite nicely compatible with those from the derivative expansion. And the second point is this question of how do we know that this scaling spectrum is sort of robust and won't change completely when we add another operator. So here there's a principle that goes into the selection for the truncation that makes the assumption that this fixed point in some sense is only as non-perturbative as necessary, or actually as sort of quite close to being perturbative, in the sense of having a near Gaussian scaling spectrum. And with this sort of bootstrap assumption, you can start building truncations, and then you can check whether that principle actually is satisfied in those truncations. And so this is work by Daniel Littim's group mostly, that shows that indeed, if you go to quite large truncations, the scaling spectrum comes out to be very, very close to a Gaussian one. And that would actually tell you that higher order operators are becoming increasingly more irrelevant, and therefore it is a quite safe assumption to make that very high curvature operators will indeed just contribute another irrelevant direction. And just as a sort of another point is that on a technical level, these fixed points are in some sense quite close to fixed points that you have in three-dimensional quantum field theories, where you can then compare results that are achieved in exactly the same technical steps, where you can compare those to, for instance, the bootstrap approach or to Monte Carlo simulations, and where the quantitative precision that you can achieve, for instance, for the Ising universality class with this technique, that is really competitive with the bootstrap. And so all of that gives us confidence that building the truncations in these ways, in this way, really allows us to have sort of robust control of the theory.
Okay, thank you. So I understand. I'm actually completely sympathetic with the iterative approach, where you kind of you just check it and you're just going to add more and more operators and see what happens. But is there, given that there's been this experience with it working so well, can it be understood in terms of there's a small parameter you're expanding in, and if so, what's the small parameter?
Yes, so the small parameter here would be the deviation of the critical exponent from its Gaussian value. So really just the deviation of these values from the Gaussian line, that would in that sense be the small parameter. And if you would start to have huge deviations from Gaussian scaling, then that would actually mean that this is no longer a robust guiding principle.
Okay, thank you.
All right, so then let me continue by actually also very clearly highlighting what the open questions in this approach are. And if you want to read more on those, we recently took a sort of critical look at the state of the art in the field and then try to really clearly point out what are the open questions and what are potential ways towards answering those. So an important one is background independence. So in quantum gravity, there shouldn't be any background, such as a flat metric put in by hand, but all backgrounds should be treated on an equal footing. And technically, that is a bit of a challenge if you want to set up renormalization group or coarse graining flows, because in order to do that, you need to know what is sort of a local patch that you're coarse graining over. And to define this local patch, you need a background metric. And so therefore, the way to go here is to work with the background field technique. And then background independence is actually encoded in certain shift ward identities. And these papers are making first steps to trying to really solve those shift ward identities. But that is one of those points that hasn't yet been completely achieved. Then the second open question, and that is, I think, a really important one, is the one on Lorentzian signature. So when I just introduced the functional renormalization group 2 slides ago, I showed you that it is set up in the Euclidean. And so what we are in some sense doing here is a quantum theory of space, not space-time. And understanding how that carries over to Lorentzian signature is one of the really critical open questions. The third important open question in this context is that of what are the propagating modes here, and are there potentially any ghost-like instabilities? And that question is motivated by the fact that there are these higher order operators that occur, that if you add them separately to the Einstein-Hilbert action, you would get potentially ghost-like instabilities. These more recent papers here show ways of constructing effective dynamics which have a bunch of these higher order terms, but which nevertheless don't feature any tachyonic instabilities. But to conclusively actually show that is what the asymptotically safe fixed point realizes, that is another one of these open questions. But as you can see here, some progress is being made on that. And so to my mind, what is really the most important question of this or any approach to quantum gravity is actually its phenomenological viability. Because even if I'm constructing a completely consistent quantum theory of gravity, that doesn't yet tell me whether nature actually chose the theory or not. And in order to connect to phenomenology, this is where matter really becomes important and matters. And so this next slide here is really quite a busy slide, and it's just meant to provide an overview, since I understand the slides will be posted online. So for anyone who would like a guide to the literature, here you can find the various papers and links to them. that show you what has been done on understanding the interplay of quantum gravity with matter in the asymptotic safety approach. And what I will do now is I'll pick out 3 examples on asymptotic safety with gravity in standard model-like systems, and beyond that I'll walk you through to give you sort of a first idea of the predictive power and how that approach could potentially be falsified phenomenologically. And the first example for that will be how asymptotic safety provides you with an upper bound on the Abelian gauge coupling. In short, the mechanism works as follows. For the Abelian gauge coupling, the beta function has a one-loop term that is positive, and then there is a gravitational contribution that is linear in the gauge coupling, where this Fg is just a way of parameterizing the effect of metric fluctuations that can be calculated in various truncations of the gravitational dynamics. I'm showing it here in the Einstein-Hilbert truncation, which has a Newton coupling and cosmological constant. And the key thing to note about this parameter is that it's constant in the asymptotically safe regime above the Planck scale. And then below the Planck scale, where quantum gravity fluctuations decouple, this very quickly goes to 0. And now, as a consequence of these 2 terms in the beta function has the following form. First of all, it starts out negative because of the gravitational term, so there's a possibility for asymptotic freedom. And then these 2 terms here sort of compete and balance at an asymptotically safe fixed point. And the structure of these 2 fixed points, that is actually what then gives rise to an upper bound on the Abelian gauge coupling from asymptotic safety. And let me explain in a little bit more detail how this upper bound arises. So in this beta function here, what that encodes physically is that matter and gravity fluctuations compete. So if you're in a regime where gravity is strong, so this term here dominates, then this negative sign here is important, which means that you're in an asymptotically free regime. So here, if you start at low energies and you sort of trace the RG flow backwards towards the UV, as soon as gravity kicks in, it bends the trajectories over towards asymptotic freedom. Conversely, if we are in the strong matter regime, where the coupling here is large, then if we again follow the RG flow backwards towards the UV, then we still run into a Landau pole as we would without gravity. And so these are sort of trajectories where we are still within an effective field theory with a finite cutoff or a Landau pole. And these 2 tendencies, they balance out at this asymptotically safe fixed point here. And this fixed point is interesting because at that fixed point, the Abelian gauge coupling corresponds to an irrelevant direction. And so there's just a single trajectory that emanates out of this fixed point, where the gauge coupling has to stay constant all the way to the Planck scale, where quantum gravity fluctuations decouple, and then there's a matter-driven flow that sets in and links this fixed point here to a particular value of the coupling at low energies. And at the same time, this predictive trajectory that serves as an upper bound for all of the viable trajectories, because beyond it, you're in this regime where you have only UV unsafe trajectories. And so if you demand that asymptotically safe gravity coupled to the Abelian gauge sector, that gives you a consistent theory, then that can only be realized below an upper bound on that gauge coupling. And so this is one of those examples where demanding quantum scale symmetry in the UV then has testable consequences in the infrared. Now, let me take that example and take it one step further towards Gauge-Yukawa systems with gravity. And the motivation to look at that is this question where the difference between the top and the bottom mass comes from. And those quark masses are, of course, determined by the Yukawa couplings. And in the standard model, those are free parameters. But of course, now in an asymptotically safe setting, it becomes interesting to understand whether that new paradigm could potentially allow you to explain some of these structures. And so here we'll proceed step by step. First, we look at the implications of asymptotic safety for a single Yukawa coupling that you can think of as the top quark, and then generalize to a top-bottom system. And then, which I will not talk about in this talk because it has a more intricate fixed point structure that takes a while to explain. where you can also see what happens under the generalization to 3 generations of quarks with mixing. And finally, to also take into account leptons is something that is work in progress. So let's first focus on a single Yukawa coupling, namely the top quark. So here actually we have a structure in the beta function that is very close to the one that we just saw for the gauge coupling. So a positive meta term and a linear term from gravity. And that term can again be calculated in various truncations. I'll focus on the Einstein-Hilbert one. And now, as a difference to the case of the gauge coupling, in the gravitational parameter space spanned by the Newton coupling and the cosmological constant, there are different regions where this Fy changes its sign. And let's look at what the consequences of that actually are. So first of all, when Fy is larger than 0, we again have a beta function that is exactly like the one for the gauge coupling that we just saw, where this free fixed point and this interacting fixed point again give a structure of asymptotically free trajectories, which can be realized below an upper bound. And that upper bound is the unique value that follows from asymptotic safety in the UV. And let me just highlight that here I don't really want you to focus on the specific numbers, the value here that is affected by the choice of truncation. So what I want to bring across here is really much more sort of the qualitative mechanisms. The quantitative numbers, as I said, are subject to systematic uncertainties. But the qualitative mechanism is that in this region here, where Fy is larger than 0, you get a finite value of the top quark mass in the infrared. So this is a region that is compatible with the observation of a massive top quark. Now, conversely, what happens if we go to this region where Fy is smaller than 0, then the beta function is just overall positive, which actually means it only has a free fixed point, which is infrared attractive, which means that you have to set the top Yukawa coupling to 0 if you want scale symmetry. And if you set that coupling to 0 exactly, there is nothing to regenerate it. It just stays 0 all the way to the infrared. And what that actually means is that a gravitational fixed point in this regime here just gives you a vanishing top mass and a vanishing Yukawa coupling, and that's incompatible with the fact that the LHC has already measured the top Yukawa coupling to be non-zero. And so that actually means that asymptotic safety, if it had a fixed point in this regime, that would not work out phenomenologically based on these considerations. So now, of course, it becomes really interesting to understand where the gravitational fixed point values lie. And with one generation of standard model matter, they lie in this forbidden region. As you add 2 generations, the fixed point moves somewhat. And then as you add a 3rd generation, it actually moves into this allowed region. And so overall, within the systematic uncertainties that the setting has, there is this sort of interesting interplay that there is a phenomenologically preferred region based on considerations of what happens with matter. And then matter quantum fluctuations appear to drive you potentially into that region.
Can I ask a question about that figure?
Yeah, sure.
So yeah, I noticed you've got a weak gravity bound at the far right. Is that something which you're putting in by hand, or is there any evidence for that conjecture being true purely within the asymptotic safety program?
Yeah, so let me clarify that this is not the weak gravity conjecture. That is related to sort of the mass of the lowest charge state. This is a weak gravity bound that says that if a gravitational fixed point would lie in this region here, it would actually trigger divergences in certain higher order matter self interactions. So it's a completely different form of weak gravity bound.
Okay, thank you.
So now that I talked briefly about a single Yukawa coupling, let me briefly highlight what happens if you generalize that to a top-bottom system. So based on what I just told you previously, you could get a finite Yukawa coupling at an asymptotically safe fixed point. But then what would actually generate the difference between the top and the bottom quark? And the answer is that they do have unequal hypercharges. And so in their beta functions, there is a different contribution as soon as you also switch on the Abelian hypercharge. And so then in this Gauge-Yukawa system, you get a fixed point relation that comes out of asymptotic safety that says that the fixed point value for the top cannot be equal to the fixed point value for the bottom as soon as an abelian hypercharge coupling is present. And in fact, the fixed point value for the top always has to be larger. And so therefore, in the far UV, this gives you sort of the correct qualitative ordering of these two Yukawa couplings. But then, of course, the question is, what happens as we flow that down towards the infrared? And here I'm showing you sort of an example setting that is very much standard model-like. And in fact, what you can see in this plot here is these two parameters, Fy and Fg, that encode the gravitational effect. And as a function of these parameters, you have these bands for the values of these three couplings. And these are broad bands around the experimental value. So those are not just sort of one sigma, those are quite a few sigma around the experimental value. But what the intersection of these three regions here is telling you is that from such an asymptotically safe fixed point, you can get sort of standard model-like systems. So you can't get the numbers of top and bottom and abelian hypercharge sort of quite exactly, but you can get systems which do have a much heavier top and which are sort of within something like 10% of the correct masses. So it's sort of a mechanism that appears to be able to give you standard model-like behavior. So now for the remaining, I think 5 minutes or so, I would now like to take this next step to say, well, of course, on the one hand, we want to check whether everything that we assume about the UV is consistent with the standard model, but can it also tell us something about things beyond the standard model, in particular dark sectors? So the standard model and gravity on their own are probably not sufficient to describe all of the observations. There's really good indications for something like dark matter to exist. And of course, we would really like to understand what the dark sector looks like. And if I'm taking a really bold interpretation of the fact that there hasn't been any discovery of dark sectors explicitly to date, then that really bold interpretation would be that it could be time for a new theoretical paradigm and that potentially might be given by asymptotic safety. So let me understand what the asymptotically safe constraints on dark sectors are. And the first question to ask is, how many new fields can you actually add? And from these various studies here, there are indications that beyond the standard model, you could add a few new scalars and fermions, but probably not too many before you lose asymptotic safety in gravity. And so therefore, we started out with the very simplest sort of vanilla model, just a Higgs portal to one singlet dark scalar. So where H is the Higgs and S is the dark scalar, and these two share a portal coupling. And now we calculated what the effect of asymptotically safe gravity on that is. The result was that quantum gravity fluctuations drive the Higgs portal coupling towards 0 at the Planck scale. So it's another irrelevant coupling that is driven towards its fixed point value at 0 under the impact of quantum gravity. That's part of a more generic or general result about asymptotically safe quantum gravity and scalar potentials. But what it actually means in the context of this dark scalar is that once the portal coupling is set to 0, it won't be regenerated. And so this dark scalar simply decouples completely if it exists. And in particular, it cannot be produced as a thermal relic. And so therefore, this quite attractive model for a dark sector with just one single uncharged scalar that appears to be incompatible with asymptotic safety. And so then, of course, you can try to take the next step and make the dark sector somewhat more complicated. And that's what we did here. So we added a dark fermion to the mix. And more specifically, what we then looked at was a toy model for the standard model, where the relevant sector of the standard model that we looked at was sort of a Higgs and a top. So there's a Yukawa coupling. There's also a non-minimal coupling of the scalar self-interaction, a mass-like term. And then there's a Higgs portal to a dark sector, and that dark sector features the same type of interactions. So this is a sort of toy model where the standard model is simplified quite a lot, and then the dark sector just mimics that. And now if you look at all of these couplings in an effective field theory setting, there's about 10 of those. All of those are free parameters. Now, what happens under the impact of asymptotic safety is that there appears to be an interacting fixed point in the system. So all of these couplings become quantum scale symmetric in the UV. And then quantum gravity switches up at the Planck scale, and we get a non-trivial RG flow towards the infrared. And quite interestingly, the result showed that except for the two mass parameters, all of these couplings correspond to irrelevant directions. And that means that the huge parameter space we would have for this model of a dark sector in an effective field theory, that shrinks quite a lot. And in fact, as a function of the dark scalar mass, you can then calculate the Higgs portal coupling, the dark fermion mass, the dark self-interaction, also the non-minimal coupling, which we didn't plot here, and the mixing angle to the standard model. So there's a lot of predictive power from that setting, whether or not this model can then really be generalized beyond a toy model to have the full standard model, whether the predictive power then remains, and in particular, whether the predictions then are actually compatible with observational bounds on relic density and so on. All of that is an open question. But what this toy model shows you is that adding the asymptotic safety paradigm to dark sectors, that could actually really narrow down the parameter spaces very considerably. So just as sort of as in the upshot of the dark matter, dark sector exploration so far, the simplest dark sector model appears to be excluded, and there could be quite a lot of predictive power in this approach that constrains dark sectors beyond effective field theory. And so that brings me to my closing slides and the future perspectives. And I think the most exciting future perspectives lie in links to various other things. The first link is that to phenomenology, to understand really the implications for the standard model, and to go beyond, understand the implications for dark sectors, and ultimately really try to understand whether there is a way to falsify these ideas about asymptotic safety by using data on low energy physics. The second important link is one to lattice approaches for quantum gravity, where some of the open theoretical questions, such as background independence and Lorentzian signature, can be tackled. And so understanding in more detail how these lattice approaches can be used to test asymptotic safety, that promises progress on these important questions. And then the last thing that I would like to highlight is the link to other settings. So in some sense, you don't have to be a fundamentalist to work on asymptotic safety, in the sense that the setting is actually compatible with the assumption that there is some fundamental new physics scale beyond which a fundamental gravity matter theory lives. That could be strings, spin forms, something completely different. And then from such a more fundamental theory, you could then at intermediate scales realize an asymptotically safe regime. And that would then imprint its predictive power on that more fundamental theory, and then potentially give you something like the standard model at low energies. So asymptotic safety in this incarnation as effective asymptotic safety could actually very well be compatible with other ideas that are being developed about the fundamental nature of gravity and matter. And so as my very last slide, let me just say that a lot of what I presented was work with PhD students and postdocs, and wouldn't have been possible with them. So let me stop the talk on a slide that gives thanks to the team. And thanks to you for your attention, and I'm looking forward to questions.